Okay, what we're going to take a look at in this vodcast is how to calculate average atomic mass. But let's just take a minute and talk about the difference between average atomic mass and the mass number of an isotope. When we're talking about the average atomic mass, we're talking about the number that appears on the periodic table, and what it represents is the average mass of all the isotopes of that element. So for example, if we're using the three isotopes of carbon, carbon-12, carbon-13, and carbon-14, if you averaged the masses of those compounds that you would find in nature, the weighted average would equal roughly 12.001. That is the mass that it would appear on the periodic table. If we're talking about the mass number, that is specific to an individual isotope. So the mass number of carbon-13 is 13. The mass number of carbon-14 is carbon-14. So when we're calculating the average atomic mass, what we're doing is essentially calculating that number that is the weighted average that shows up on the periodic table. When we do that, we're going to use a pretty simple formula. And the formula for calculating average atomic mass is average atomic mass is equal to the percentage of one isotope times its mass, or its mass number, plus the percentage of the second isotope times its mass for however many isotopes you have. So if you have three isotopes, you would add another percentage and another mass. This is a weighted average. It's not a regular average. If you were taking the average of two numbers, you would add them up and then divide by the number of numbers present. So you would divide by 2. You don't do that with average atomic mass. Since it's a weighted average, you're simply using that percentage and the mass. So let's take a look at a few problems here. What is the average atomic mass of iodine if it contains three isotopes with abundances of 80%? Oh, let me get a pen. Of 80%, 17%, and 3%. So let's set up the equation. Average atomic mass is equal to, now we want to do 80% times the mass number 127. And remember, when we write percentages in decimal form, you simply move the decimal place over 2 places to the left. That's the same as dividing by 100, because you want to put the percentage in decimal form when you use it in a math problem. The second isotope is 17%, so we're going to move that decimal place over 2 places. That isotope has a mass of 126. And then the third isotope is 3%. Now when we move the decimal place over 2 places, we've got to put a 0 there as a placeholder. So we've got 0.03, which is 3%, and its mass is 128. So what we're going to do there is the math. So take out your calculators, and we will take 0.8 times 127 plus 0.17 times 126 plus 0.03 times 128. And we get 126, so we get 126.86, and that would be the average atomic mass of the element iodine, which has individual isotopes of those masses and those percentages. Again, it's very important to understand that would be the number that would be reported on the periodic table. Those would be the mass numbers of the individual isotopes that make up the element iodine. Alright, let's take a look at another type of problem. Let me get a pen. It says, what are the percent abundances of an element iron? So right away we can just write iron. If its average atomic mass is 55.85 AMUs, And the two isotopes that make it up are iron 55 and iron 56. Now we've got a little bit of a twist. If you remember, our formula is percentage times the mass of the isotope plus the percentage times the mass of the isotope. So we've got our mass numbers 55 and 56, so we can put those there. So the one isotope has a mass of 55. The other isotope has a mass of 56. Now the question becomes, what are the percentages? Well, the two percentages have to add up to 100%, which is the same as, well, I shouldn't say it's the same. When we write that in decimal form, we write it as 1. So if we call the one percentage x, the other percentage has to be 100% minus x, or 1 minus x. It doesn't matter which one we call x. We could just as easily have called this one x. My pen's not writing. And then we could have called this one 1 minus x, and we would still get the same answer. So if we do the problem here, we've got 55.85 is equal to 55x plus, and we're going to distribute 56, distribute that, minus 56 times x. So if we do the math here, 55x minus 56x is going to give us negative 1x. 55.85 minus 56 gives us negative 0.15. If we solve for x here, we would get 0.15. Now remember, that x is, or that 0.15 is that percentage in decimal form. So that if we move the decimal place over 2 places, that would mean that isotope is 15% of the compound. So that isotope there would have to be 85%. So again, if we had called that one x and that one 1 minus x, we simply would have gotten x equal to 0.85, and then that one would have been 1 minus 0.85. Alright, let's take a look at one more type of problem. Let me reload my pen. Alright, this is another way of doing these problems. It says if carbon has an average atomic mass of 12.04 and its one isotope is carbon 12, so right away we know the mass is 12, and that accounts for 98% of the isotopes, so we'll put that as 0.98. It says what's the mass of the other isotope? So now we're looking for that unknown mass, and if that's 98%, this percentage would have to be 2%, which would be 0.02. So now we've got this problem where we're solving for the unknown there. So I am going to take 0.98 times 12, and that's going to give me 11.76 plus 0.02x, and that's equal to 12.04. I'm going to take 12.04 minus 11.76, and I'm going to get 0.28 is equal to 0.02x, and then I'm going to solve for x there, 0.28 divided by 0.02, and I get x is equal to 14. So my value for my missing mass would be 14. Okay, so just as a reminder, as a quick review, when we're finding average atomic mass, that is the number that appears on the periodic table, and it would be the average of the isotopes of that compound. The mass number is going to be the mass of an individual isotope.